Southern California, 15,000 years ago. The air is cooler than it is today. The Los Angeles Basin is a wet, fertile plain threaded with streams. Colombian mammoths browse in the lowland scrub, 13 feet at the shoulder, 10,000 pounds each. Beneath them, deep in the crust, two tectonic plates have been locked together for over a century. The stress stored along that boundary has been building since before these animals were born. When the fault finally breaks, it will rupture across hundreds of miles in seconds. Dozens of feet will offset the ground. Rivers will be severed from their own channels. Entire hillsides will collapse. No human being will record any of it. The 1906 San Francisco earthquake, magnitude 7.9s, is the most famous seismic event in California's history. Yet, the prehistoric ruptures buried in the geological record were worse, and they happened again and again. The scars left by those prehistoric ruptures are still in the ground. Over the last 50 years, a discipline called Paleoseismology, the study of ancient earthquakes through geological evidence, has learned to read them. The work starts with the engine that produces the quakes in the first place. California sits on the boundary between two of the largest tectonic plates on Earth. The Pacific Plate, carrying the ocean floor and a strip of coastal California, moves to the northwest. The North American Plate, carrying the bulk of the continent, moves to the southeast. They meet along the San Andreas Fault, a fracture roughly 800 miles long, running most of the length of the state. The plates grind past each other horizontally, making the San Andreas a transform fault, specifically a right lateral strike-slip fault, meaning the far side of the fault always moves to the right relative to an observer. This motion has been continuous for roughly 30 million years at a rate of about 1.5 to 2 inches per year. That is approximately the speed at which human fingernails grow. 2 inches per year sounds negligible. It is not. Over a century, it adds up to roughly 15 feet of displacement. Over a million years, 30 miles. Over 30 million years, hundreds of miles. Rocks that formed side by side in Southern California, deep in the geologic past, now sit far to the northwest, separated by the full length of the state, carried there incrementally on the back of the Pacific Plate. The landscape of California has been physically torn apart by this motion. Rivers, valleys, and mountain ranges that once aligned across the fault have been dragged out of position over millions of years. The San Andreas is not a crack. It is a conveyor belt running through the middle of the state. The fault does not behave the same way along its entire length. In parts of central California, the plates slide past each other in a slow, continuous creep. Thousands of tiny earthquakes occur here constantly, most too small for anyone to feel. The energy dissipates gradually, released in micro increments that never accumulate into anything dangerous. These creeping segments are not the threat. They are, in a sense, the fault working as intended, bleeding off stress in real time instead of storing it. The locked segments are. In northern and southern California, the friction between the plates is so high that the fault seizes completely. The plates keep pushing at the same rate, but the fault does not move. The crust on both sides bends under the strain. Energy accumulates invisibly. Year after year, decade after decade, sometimes century after century, the stress grows. Geologists describe this process with a concept called elastic rebound. The crust stores tectonic energy the same way a wooden stick stores kinetic energy when you bend it over your knee. The stick flexes, it absorbs force, then it snaps. When the friction on a locked segment finally fails, the rock lurches back to its original unstressed shape in seconds. All the accumulated energy detonates at once. The longer the fault has been locked, the more energy has built up, and the more violent the snap. A magnitude 8.0 earthquake is what happens when centuries of stored tectonic stress release simultaneously. If a massive prehistoric earthquake left no written records and no standing ruins, how does anyone know it happened? The answer is buried in sediment. Soil and organic material accumulate over time in horizontal layers. Mud settles on top of sand. Peat and decayed plant matter grows on top of mud. Charcoal from a forest fire washes in on top of peat. The oldest layers sit at the bottom, the youngest sit at the top. Geologists call this the principle of superposition. When a major earthquake ruptures through these stacked layers, it tears them apart, snapping, offsetting, and displacing the sequence. Then time resumes. Wind, rain, and floods deposit new, undisturbed sediment over the damage. The rupture is sealed inside a geological time capsule waiting for someone to cut it open. In the 1970s, a geologist named Carrizo went looking for these capsules at a site called Pallet Creek, northeast of Los Angeles. The location was ideal. For thousands of years, local swamps and streams had deposited alternating layers of dark, organic-rich peat and light-colored sand and silt. A high-contrast record, easy to read visually. CA ordered backhoes to dig deep trenches perpendicular to the fault line. The trenches were 10 to 15 feet deep, cutting straight through the layered sediment. Researchers then used trowels and brushes to scrape the trench walls perfectly smooth, laid grids of string across the exposed face, and photographed and mapped every centimeter of the soil layers. They were looking for terminations, the exact point where a fault line cuts through the lower layers but is buried by an upper unbroken layer. That boundary is the earthquake. What C found at Pallet Creek was not one boundary but dozens. Distinct rupture events stacked in stratigraphic sequence, extending back over 1,200 years. Each rupture was discrete. A moment when the earth broke, sealed above by the quiet years that followed. Pallet Creek proved that catastrophic earthquakes on the San Andreas were not rare anomalies. They were a repeating rhythm. Finding the break is step 1. Dating it is step 2. Scientists cannot date the dirt itself. They date the organic material trapped inside it. A layer of peat contains dead plant matter. Charcoal contains carbon from burned wood. Both contain carbon-14, a radioactive isotope that decays at a known measurable rate. Scientists carefully extract these organic samples from the trench wall with tweezers, bag them, and send them to a laboratory. If a ruptured peat layer dates to 1,200 years old and the undisturbed sediment sealing it above dates to 1,100 years old, the earthquake struck within that 100-year window. This is radiocarbon dating, the primary clock of paleoseismology. The technique does not give an exact year, it gives a bracket, but a bracket is enough to build a timeline. The Carrizo Plain is a long, arid valley in central California, largely uninhabited. It contains the most visible surface expressions of the San Andreas Fault anywhere on Earth. When paleoseismologists applied the same trenching and radiocarbon methods here, the timeline they assembled was worse than Pallet Creek had suggested. Between approximately AD 1218 and 1510, at least 4 catastrophic earthquakes ruptured the southern San Andreas in rapid succession. One event, labeled Event B, dated to roughly AD 1405 to 1510, offset the ground by 23 to 36 feet in a single rupture. 3 earlier events labeled C, D, and E struck between AD 1218 and 1405. The average gap between these massive quakes was only 73 to 116 years. That number matters. The popular assumption about major earthquakes on the San Andreas is that they arrive on a roughly predictable schedule, one major rupture every 250 years or so. The Carrizo Plain data directly contradicts this. During the medieval cluster, the fault was producing catastrophic ruptures 2 to 3 times faster than the assumed average interval. Scientists describe this pattern as a seismic supercycle. The fault does not discharge its accumulated stress in one neat, evenly spaced event. It can fire off a rapid sequence of massive ruptures within a few centuries, then fall silent for hundreds of years before the next cluster begins. The quiet period between clusters creates a false sense of regularity. The cluster itself is the dangerous phase, and it arrives without announcement. Digging deeper into the Carrizo Plain stratigraphy revealed still older events. Ruptures labeled F and G pushed the record past 200 BC. To understand the scale of these ancient ruptures, scientists use a modern baseline, the 1857 Fort Tejon earthquake. That quake struck on January 9, 1857, with an estimated magnitude of 7.9. It ruptured 225 miles of the southern San Andreas. The ground offset by up to 30 feet in places, trees were uprooted, rivers sloshed out of their banks. The shaking lasted approximately 3 minutes. Because California was sparsely populated in 1857, only 2 people died. But the geological scars were immense. Scientists know exactly what a 7.9 looks like in the sedimentary record. When they compared that baseline to some of the prehistoric Carrizo Plain signatures, the older events looked worse. Several show characteristics consistent with super shear rupture. A quake where the fault tear propagates faster than the seismic shear waves it generates. In a standard rupture, the tear unzips at roughly 2 miles per second. In a super shear event, the tear outruns its own vibrations, producing a concentrated shock wave along the fault, the geological equivalent of a sonic boom. Localized ground shaking during a super shear event is amplified far beyond what standard seismic models predict. A magnitude 8.0 plus earthquake does not just shake the ground, it redesigns the landscape permanently. The clearest monument to this process is Wallace Creek, also in the Carrizo Plain. From the air, the creek looks like a glitch in the terrain. Water flows straight downhill from the Temblor Range, hits the San Andreas Fault, makes a sharp 90-degree turn, runs parallel to the fault for 426 feet, then makes another 90-degree turn to resume its downhill path. The water did not choose this route, the fault imposed it. Each time a prehistoric earthquake ruptured the San Andreas, the Pacific Plate shoved the downstream half of the creek further to the northwest. Individual quakes contributed offsets of 30 feet or more in a single event. Over thousands of years and dozens of ruptures, the total displacement reached 426 feet. Wallace Creek is a monument to cumulative prehistoric violence, measured in the geometry of flowing water. The same process creates what geologists call beheaded channels. A small stream crosses the fault. A single 30-foot offset during one earthquake severs the downstream section from its uphill water source. The lower channel dries out and becomes an orphan valley, a dead riverbed with no river. The upstream water is forced to carve an entirely new path. California is full of these dry, severed prehistoric stream beds, each one the signature of a specific ancient rupture. Where the San Andreas bends, the plate collision produces additional features. At restraining bends, where the fault geometry forces the plates to compress during a rupture, the crust buckles upward, thrusting new hills and ridges into existence in seconds. These are pressure ridges, hills that did not exist before the earthquake and that owe their entire topography to the violence of a single event or a series of events on the same bend. At releasing bends, where the geometry pulls the plates apart, the ground between them drops, creating depressions. Water fills these depressions over time, forming sag ponds. Some of California's natural lakes sit directly on the fault trace, occupying basins that were torn open by the violent pull-apart geometry of prehistoric ruptures. Every one of these features, the offset creeks, the orphan valleys, the ridges, the pond's physical record of a specific prehistoric earthquake or sequence of earthquakes, written directly into the topography. Finding these features used to require walking the fault on foot through dense chaparral and redwood forest. Today, paleoseismologists use LiDAR, light detection and ranging. Lasers fired from aircraft pulse the ground millions of times per second, measuring surface elevation with centimeter-scale precision. Algorithms strip away trees, brush, and buildings to produce a bare earth model of the terrain beneath. On a LiDAR map, the offset streams, scarps, pressure ridges, and sag ponds left by ancient earthquakes become immediately visible, features that were invisible at ground level, revealed all at once from above. LiDAR tells scientists exactly where to dig their trenches. The Carrizo Plain events occurred within the last 2,000 years, but the San Andreas has been active for 30 million. 15,000 years ago, the locked segments of the fault were accumulating and releasing stress on the same cycle, through the same mechanisms, into a Southern California landscape that looked nothing like the modern state. The climate was cooler and wetter than it is now. Rainfall was higher. Grasslands and woodlands covered areas now classified as semi-arid scrub. Streams and marshes fed a rich lowland ecosystem below, and the animals that inhabited this landscape were enormous. The largest animals on the plain were Columbian mammoths, the tallest land mammals in North America at the time, weighing close to 10,000 pounds each. The saber-toothed cats, Smilodon fatalis, carried heavily muscled forelimbs built for pinning large prey to the ground. Dire wolves hunted in packs, larger and heavier than modern gray wolves. Giant ground sloths of the genus Paramylodon weighed over a ton, their hides reinforced with bony nodules that functioned as built-in armor plating. All of them occupied the same landscape that the San Andreas Fault was quietly tearing apart beneath their feet. When a major rupture triggered, the first sign was sound, a deep, sourceless roar rising from underground. The P wave, a compressional wave traveling at roughly 3.5 miles per second through the rock. The P wave carries acoustic energy. For the megafauna, the earthquake announced itself not as shaking but as a sustained, a low-frequency thunder rising from the dirt with no sky to explain it. Animals would have frozen. Seconds later, the S wave arrived, the shear wave. The S-wave rolls and snaps the ground laterally, producing the violent back-and-forth motion that collapses structures and topples heavy objects. At magnitude 8.0, the ground accelerations are severe enough to throw a 10,000-pound Colombian mammoth off its feet. The shaking could last for 2 to 3 minutes. For an animal with no understanding of what was happening, standing on ground that had been stable its entire life, those minutes would have been pure sensory chaos. The secondary hazards were worse than the shaking itself. In the wet, marshy lowlands of prehistoric Southern California, the sustained vibration would trigger liquefaction, a process where water-saturated soil loses its structural integrity and behaves like a liquid. The ground does not open up, it stops being solid. Any heavy animal caught in a liquefaction zone would sink under its own weight. A giant ground sloth weighing over 2,000 pounds standing in a marsh that had been firm ground 3 seconds earlier would find itself mired with no way to extract its own mass. Herds of ancient bison crossing waterlogged flats would face the same trap across a wide area. The heavier the animal, the faster it sank. The wetter the ground, the worse the liquefaction. Pleistocene California had plenty of both. In the mountains, the San Gabriel Range, the Temblor Range, the shaking sheared cliff faces loose. And millions of tons of rock and solid soil would avalanche into valleys burying everything below. Landslide debris damming rivers would create sudden flood zones behind the blockage, inundating valleys that had been dry ground minutes earlier. The La Brea tar pits in modern Los Angeles sit at an intersection of paleoecology and tectonics. The asphalt, thick crude oil seeps to the surface through fissures in the Earth's crust. Those fissures are products of California's deeply fractured geology. A major prehistoric rupture on a nearby fault could shift the subterranean plumbing of the Los Angeles basin, snapping open new fissures and causing asphalt to pool in new locations along established megafauna corridors. Old seeps could seal shut while new ones opened. The sticky surface of a fresh seep, camouflaged by fallen leaves and pooled rainwater, would trap any animal that stepped on it. A panicked herd of ancient horses stampeding through aftershock tremors could blunder directly into one of these newly active traps. The tar pits are not a paleoseismic dating tool. Scientists cannot use them to pinpoint when a specific earthquake occurred. But the pits are a consequence of the same tectonic fracturing that generated the prehistoric big ones. The faults created the fissures fed the seeps. The seeps killed the megafauna. The deepest layers in the Carrizo Plain and Pallet Creek trenches pushed the earthquake record past 2,000 years. Events F and G, dated before 200 BC, represent some of the oldest ruptures positively identified on the southern San Andreas. Their signatures in the trench walls suggest offsets and rupture energies that exceed anything in the more recent medieval cluster. Several of these ancient events show ground deformation patterns consistent with supershear behavior. The identification is an inference. No seismometer existed to record the wave speeds, but the preserved damage pattern matches the focused, amplified shaking that supershear ruptures produce. If the inference is correct, these are among the most violent earthquakes the San Andreas has generated in the last several thousand years. Or radiocarbon dating brackets these ancient events within windows of decades to centuries. Useful, but imprecise. A second forensic tool can sometimes sharpen the resolution to a single year. Dendrochronology, the study of tree rings, reads seismic trauma directly from wood. Trees add one growth ring per year. The width of that ring reflects the growing conditions of that specific year. A massive earthquake can snap the crown off a tree, permanently tilt its trunk by destabilizing the soil beneath its roots, or tear its root system in half where the fault crosses beneath it. The tree survives these injuries, but its growth is severely stunted, sometimes for decades afterward. A core sample drilled from an ancient tree or preserved stump will show hundreds of normal thick rings followed by a sudden cluster of compressed and thin rings marking the onset of trauma. If multiple trees distributed along the fault line show the same growth suppression beginning at the same ring, scientists have a dated earthquake, pinned to a specific year, confirmed by independent biological witnesses spaced miles apart along the rupture. North of California, along the Cascadia subduction zone, prehistoric earthquakes dropped entire coastlines several feet in seconds. Forests of coastal red cedar that had stood above the tide line were plunged into salt water and killed instantly. The dead trees, called ghost forests, still stand in the coastal mud, stripped of bark, bleached white. Their final growth rings preserve the exact year the ground dropped and the ocean rushed in. And as these ghost forests are among the most precise natural timestamps for prehistoric seismic events anywhere in the world. Entire stands of dead timber, rooted in place, marking the moment, an earthquake redrew the coastline beneath them. The Paleoseismic record does not give California a schedule. It gives California a pattern, and the pattern is not comforting. The Palette Creek and Carrizo plain data show high variability in recurrence. Massive ruptures have arrived as close as 50 years apart and as far apart as 300 years. The seismic supercycle model, clusters of rapid-fire catastrophic quakes separated by long quiet periods, fits the data better than any fixed interval. The fault accumulates tectonic debt over centuries and pays it off in a flurry of massive ruptures spanning a century or two, followed by generations of silence. The popular idea that the San Andreas is overdue for a major quake assumes a regularity that the prehistoric record does not support. The fault does not operate on a timer, it operates on a stress budget. The quiet period between clusters feels like safety. The geological record says it is a pause. The Pacific Plate and the North American Plate have not stopped moving. They have not slowed down. The 1.5 to 2 inches per year of motion that has driven every prehistoric rupture on the San Andreas continues today, exactly as it has since the fault formed. The locked segments are still locked, still bending, still storing energy at the same rate they always have. Every year of silence adds another increment of stress to the system. California's modern highways, aqueducts, power grids, and cities cross the exact same fault traces that prehistoric earthquakes offset by 30 feet at a time. The infrastructure is decades old. The engine underneath it is 30 million years old. And the paleoseismic record is clear on one point. The engine has never taken a permanent break. It has only taken pauses. The mammoths are gone. The saber-toothed cats are gone, the fault remains, and it does not keep a calendar.